so here we are back over in Blender. So the first thing I'm going to do is switch over to my scripting layout by selecting scripting across the top here from my different list of workspaces. So I've hit scripting. Now we're over in the scripting panel. Okay, so I've rearranged mine slightly because I don't need this console here, so I can drop that down and make my 3D structure nice and big here. So this on the right hand side is the scripting window, the text editor, and so this is the final code that we're going to write that allows us to visualize the structure. So if I just run this code on the structure as is, you'll see what the end result is going to be. Now, this is the code you can run provided you have somewhere within this file path here, right? So for me, I've just left them on my desktop. You've got the vertices CSV file, which you generated when we exported the data for this structure. Okay, so that just gives the location of each of the vertices in 3D space. You have the edges CSV file, and that just gives the definition of each edge within our structure. And so that's just a vertex number on each end of each element. And then the only other thing that we need for this to work is the member color CSV file that we literally just exported from our Jupyter notebook. So provided you've got all of those three files and your code can see them, they're in the right location based on what path you've provided. If we run this now, we can see our structure. Okay, and so there you have it. I mean, that's the end result, right? So that's remember, we're using the jet color map now, where the blue is the tension, red is compression, and all the colors in between are some force in between, basically. And I just think that makes for a nicer visualization, certainly on a larger structure than the seismic color map. But it's up to you. You can use whatever color map you like. You'll notice over in the outliner here, I now have a hierarchy, a new hierarchy, a collection. Collection is the word I'm looking for. So I have a new collection called structure, and that is that's the structure we just generated. So I can toggle that on and off. Now you'll notice here I've imported vertices. Okay, so that was the original locations, the undeformed locations of my vertices. I could equally change that. I could get rid of vertices and I could put in the deflected vertices CSV file that we also generated at the end of our Jupyter notebook, and I would get obviously the deformed shape of our structure. So it's entirely up to you. You can visualize the axial, or rather the colored in members, the axial forces based on the undeformed structure or the deformed structure, depending on which vertices CSV file you pass in. Now I can also, let me see, come on down here to where we're actually calling the function. If I change that to, that's a sort of a scale factor, let's change that to 3 and run this again. In fact, let me just delete that hierarchy first, and let's run this again, and you can see that we get the scale of the elements has changed. It's essentially a smaller scale because that's changed from 0.07 to 0.03. So again, you can play around with that as well. So these other parameters, this 10 and this false, we'll see what they mean as we progress through the code. But that number there actually is governing the sort of scale of the individual elements. So let's again right click on that and delete hierarchy. Let's bring up let's go with a new file, and let's call this rebuild _ tutorial. Okay, so what I want to do is basically rebuild my way back up to that code and explain along the way how we do it. All right, so I'm going to try and keep the actual typing to a minimum and copy and paste things in as I go, just for speed's sake, to be honest. Right, so let's bring in a whole lot of imports, right, to start things off, right? So what am I doing? Import and BPY, that's the usual you have to bring in every time. CSV, NumPy, this gen from text utility that I always use to import CSV files into my Python. Math utils, just the utilities, some mathematics utilities, and the math library, and then I'm importing matrix from math utils so I can make a reference directly to matrix, and we're going to need that as we progress through. So they're just the bits and pieces that we need to bring in. Right, how are we going to do this? The way I want to do this is I want to have one main function that gets called. That main function is basically going to hold all of the logic that is required to go and step through the various different steps to rebuild our structure. So there's going to be a main function, so we can sort of build it up like this, right? So let's say at some point we're calling a main function. That main function is going to have parameters, right? So we're going to just use the same parameters that we saw in the sample file, right? So the first number there was 10. Don't worry about what that 10 is. The next one was 0.03. We know what that is. That's the scale of the individual elements. And then what was the last one? The last one was a Boolean, which we set to true. In fact, let me set that to false again. You don't know what that means yet, but I'll get to it. So that's the function that that we're going to call. Now, in order to call it, we must first define it. So let's define main, and at this point we will pass in. So what have we got? We've got the first one, which I'm calling chunk size. The next one was element scale, and the final one was redraw. Okay, so in essence, what do these mean? Well, we know what element scale does. That needs to be a lowercase d. Okay, so element scale was just the scale of the individual elements. Chunk size. Now, what you'll find, which is what I found when I was writing this, coming up with this code, was if I have a very large structure with lots and lots and lots, hundreds, thousands of elements, if I try and generate a new element within Blender, or rather a new object, using Blender's terminology, a new object in Blender, for every single one of those structural elements, the code slows down very fast and really struggles to run. I won't claim to have written the most efficient code in the world, but it really becomes extremely slow if you try and keep each structural element as an individual object. And so the way I got around that was I merged all of my objects into a single mesh, into a single object periodically throughout the while we're cycling through all of the members. So we cycle through each of the members, generate a new member, generate a new material, and then every time we hit whatever number chunk size is, we take all of the elements and we merge them into one. So I set chunk size to 10 here, right? So what that means is for every 10 new elements we create, we sort of pause and we merge all of those elements into one mesh, and then we go along and we generate 10 more and merge it into one mesh, and that way it keeps the code ticking along quite quickly, because Blender is really efficient with objects that have very, very large numbers of vertices within them, but when you start splitting those into individual objects, things slow down very, very quickly. So that's what chunk size is. Redraw, that was just basically a true or false. If it's set to false, which it is now, the 3D view will not update until all of the elements have been created. And that's, to be honest with you, that's probably the most efficient way of doing things. But because I wanted to have a nice way of visualizing this thing sort of emerging and being built, you can set that to true, and it will redraw the 3D viewport and update the 3D viewport every time a new element is created. Now that's a lot slower, right? So I'm not suggesting you would do that for larger structures, but if you have a medium-sized structure and you want to kind of see the structure kind of emerging, if you saw the preview video to this tutorial that I put out, I did exactly that. I set redraw equal to true, and for a large structure you could see the structure emerging element by element. Now that was really, really slow, and in fact in the video that I recorded for that, I actually sped that up, and you'll see yourself if you try and do that for larger structures, it's really quite slow. All right, so that's the main function set up. So now we've got a main function defined. We're going to basically we're going to lay out the various different steps that have to be completed. Now I'm going to make reference within this main function, I'm going to make reference to other functions which I have not yet defined. And so it won't run, but we'll define them sort of as we progress. Right, so the first thing I need to do is to import my data. So I'm going to call a function which I haven't written yet, called import data. It doesn't need to take any arguments, and that can be equal to, it's going to return edges, vertices, and color. Or in other words, whatever it returns, whatever that function returns, is going to be assigned edges, vertices, and color. Okay, we've got to write that function. So in fact, why not go ahead and write that now? And so again, in the interest of everyone's sanity, I'm just going to paste it in. In fact, I should probably zoom in a little bit here, make this easier to read. Okay, so what have I got? I've defined a function called import data, and I'm just basically calling gen from text. I'm passing in the file path and the delimiter. This is the standard import code that we use throughout the course. And we're assigning the output to vertices. We're doing the same thing and importing our edges CSV, assigning it to edges, and the same thing for color. And then we're returning out of the bottom of this function edges, vertices, and color, all standard stuff. So that was the first thing. Next, we want to generate or set up a collection. So back down within our main function, let's have a little note. Let's have a little note here that just says collection setup. I'm going to generate a new collection. So over in my hierarchy here, I want my structure to be, or all the elements of my structure to be generated inside of a collection that I'm going to call structure. So I'll just use Blender's standard API functionality to do that. So I'll say bpy.data.collections.new, and I'm passing in the name of the collection, and I can get a handle to that collection by letting this equal to call. So now if I want to have access to that collection, the handle to it, to get access to it, is call, C-O-L-L, name it whatever you like. Call for collect, short for collection, obviously. Now the next thing I need to do, if I run this, it will generate a new collection will be generated, but it won't appear in the outliner here, because in order for it to appear over here, it has to be linked to the master collection or the scene collection. So again, using some of Blender's standard functionality, we can do that next. Okay, so there we are. So bpy.context.scene.collection.children.link, and then we're linking in the collection. So that's being linked to the master collection. So now if I run this code, well, what's it going to do? It's going to import all this data for a start, but then you'll also see that it runs these two, which puts a collection over here. So let's try that. Okay, there you have it. So there's our collection that we can then generate all of our elements within. Now that we've got the collection set up, let me just get rid of that, because that's going to, the next time I run this, we're going to duplicate that. So next what we want to do is generate our individual elements. So we're going to cycle through each of our elements. I'm going to establish a counter here that I'm going to use. I'll call it CNT equal to 0. And now I'm setting up a for loop to go through each of my elements. I'll have an iterator which will let equal to n, which goes up by 1 for every time I come through. E is going to be the current value of the edge. And that's going to be enumerate edges. Okay, so this is going to allow me to cycle through each of the edges that I've imported. I'm going to pull off the position of node I for the edge, and that's going to come out of vertices. That was also imported, remember. So I need to reach into vertices, and I need the number that is located at, it's located at E0, so the current edge, the number at the current, for the current edge, remember that's going up by 1 for every time we come through edges. So the number for the current edge at position 0, minus 1, because we're indexing into it. Let me see, and then I want that to be recast as an integer rather than a float. I think it comes in as a float. So that's identifying the correct row within vertices, and I want all of the columns within that row. Okay, so that's the position of the edge, or that's the position of the vertex that defines the first or one side of the current edge. Okay, pause I. Right, let's do the same thing for the position of the vertex on the other side. Let's call that pause J. Vertices, and that's going to be 1. Okay, so now we have the position. Let's imagine we're dealing with, let's go to edit mode here. Let's imagine we're dealing with this edge, right? What I've done is I've just identified the position of this vertex and this vertex at I and J. So the next thing that we need to do, this is really the meat of it, right? We can generate we're going to generate cylinders, right, to represent the elements. We can generate a cylinder, that's fine. We can use Blender's standard functionality to do that. And if we do that, we call the code to generate a cylinder. We'll get a cylinder located at the origin here, right? Default size, default number of vertices, but it's going to be positioned down here. The trick and the bulk of the work in this entire code is really about taking that default cylinder and moving it to the position and orientation of the relevant element. So let's say we're cycling through all the elements here, and I'm working on this one currently. Well, my task now is to get a cylinder that gets generated at the origin down here, right? So in fact, if I was to, let's tab out of that, let's go Shift A, Mesh, and Cylinder, right? If I call a cylinder, that's what I get. I now have to, via the code here, take that cylinder, I have to orientate it to match the orientation of this element, right? I've got to change its length so it's the same length as the element, and then I've got to translate it so it's in the position of that element. So they are the operations I have to do. Now, within 3D space, the position, orientation, and scale of any element, of any structure, can be captured in one very important matrix, right? Sometimes it's called a transformation matrix. I think in Blender, it's in the Blender documentation, it's called a world matrix. But essentially, the transformation matrix is a 4x4 matrix which encodes within a given reference frame, right? So for us, this is the global reference frame. So within a global reference frame, this transformation matrix encodes the position, orientation, and scale of an element. So it's packed full of information, and it is all of the information we need to take this cylinder and morph it to be representing any one of these elements. Okay, so perhaps I'll edit in a side discussion here of me giving you a bit of a primer on the transformation matrix. Okay, so future Sean jumping in here just to provide a little bit of additional context around this idea of a transformation matrix. I'm not going to try and give a full description or lecture here on the transformation matrix. I just want to explain the components of it that are very specifically relevant to our discussion here around the position and orientation of these 3D elements. So what you're looking at here is an example of a template, if you like, for a transformation matrix. So we said it was a 4x4 square matrix. Now this transformation matrix encodes the position, scale, and rotation or orientation of our particular 3D element. Now I'm not going to dwell too much on the scale here. I just want to focus on the orientation and the position. So you might recognize this bit here is actually the rotation matrix for our element, and this bit here is the translation or the position of our element. And we can think about this piece down here as kind of just filler. That doesn't change anything. What it just expands our matrix to be a 4x4. So all of the magic is, if you like, is happening in this box and this box. So let's just pick these apart a little bit here, right? So we said that this 3x3 in the top left corner was the rotation matrix. So it's the rotation or orientation of our element within a global reference frame. That's what's being communicated in this 3x3 top left matrix. All right, so let's have a little look at that matrix on its own here. Okay, so what this actually is, one of the ways you can interpret this you can interpret these columns as the vectors of the local x, y, and z axes represented within a global reference frame. So let me first of all write a note on that, and then I'll kind of demonstrate what I mean by that. So this first guy is the local x vector represented in a global reference frame. This is the local y, and this guy is the local z vector. Okay, and just before we go too far down that rabbit hole, let me just put a little note out here just to say that this is the translation or the position of the element within a global reference frame. And when I say the position of the element, I mean the position of the reference point on the element, and that's typically going to be in the geometric center of the element. So any element that we generate within Blender, it will have an origin point or a reference point that's located at the center, the geometric center of the mesh that was created for that element. So let's sort of illustrate this idea around the transformation matrix, or the rotation matrix, I should say. The transformation matrix itself is pretty straightforward. So let's imagine we're in a world here where we have a global x. Let's say xg for x global. We have a global y, we'll say yg, and a global z. So that is the global coordinate system. Now we want to be able to represent the orientation of any element within this global coordinate system, and we do that with this rotation matrix. Let's see an example with some numbers here. So let's imagine we're dealing with an element. So I'll just say, consider an element that's orientated along the global x-axis, that lies along the global x-axis. All right, so let's just sketch this thing out. So let's say we've got some kind of a cylinder here, and we'll imagine that this end of the cylinder is end I, and this end of the cylinder is end J, and there's a reference point is going to be the center of the cylinder, halfway between I and J. So that's the position that we're going to shift our cylinder to from the origin. Now let me, for demonstration purposes here, let me just take that and move it down here, let's say. For our elements, we're defining the local z-axis as running along the member from I to J. So that's the local z-axis. Let's call that z local. We're defining, this element isn't vertical in this case, right? So we're defining the xz plane as a vertical plane. Okay, so in order to determine the xz plane, what we end up doing is taking node I and offsetting it vertically, and taking node J and offsetting it vertically by 1 meter. And that means we've got the coordinates of this point and this point, which means we can get the coordinates of this point. Okay, and through a little bit of clever matrix manipulation, we can once we've defined that plane, that vertical xz plane, we can define a vector which is orthogonal to the z vector, and we're going to call it, let's go with red, that orthogonal vector is going to be the local x vector. We'll say xl. Okay, and then we can take the cross product of those two orthogonal vectors and get the mutually perpendicular vector, which we're going to call the local y vector. Okay, so we can construct this this orthogonal reference frame by just knowing the coordinates of node I and the coordinates of node j. So we can build this reference frame that is local to the system, to the element, I should say. So now we need to represent these three unit vectors, xl, yl, and zl. We need to represent those within this global reference frame. Well, what does that mean? Well, let's go vector by vector here. Let's take xl for a second, and let's say we want to represent that. It's a unit vector represented in the global reference frame. So what does that mean? Well, if I take this vector here, right, in a global reference frame, it's a vertical vector. So it's aligned along the global z. So it has 0 component in the global x direction, and it has a 0 component in the global y direction, because it's a unit vector and it's perfectly aligned along the global z axis, right? And it's also pointing in the same direction. And so if I want to represent that local x vector in the global z-axis, okay, well, what's its x component in the global reference frame? 0. What's its y component in the global reference frame? 0. What's its z component in a global reference frame? Well, it's going to be 1, isn't it? Okay, and that's fine. So that's the first column of my rotation matrix. Then we go and we look at y local. Let's represent that. Well, it turns out in this particular case that y local is perfectly aligned along y global, right? So they match. So the component of y local in the global reference frame, its x component is going to be 0, okay, because there's no component of this local y vector in the global x direction, right? You don't need to specify any x component in order to build this y local vector. So it's going to be 0. It's going to be 1 in the y direction, and it's going to be 0 in the z direction. Again, simply because y local is aligned perfectly along with y global. All right, that's the second column. And then we can say, well, what's the z? So z local is aligned along x global here, right? And so if I want to represent z local in a global reference frame, it's going to be 1, 0, and 0. Again, because z local perfectly aligns along x global. So when your local reference frame lines up with your global reference frame, even if the axes are swapped around, you end up with a rotation matrix that looks like that. But once we build the algorithm that allows us to build this rotation matrix based on that coordinate and that coordinate, well, then these coordinates I and j can change to whatever we like, and we can, again, pretty easily build up this rotation matrix. It won't have ones in it. It will have, values less than 1, because in each case, this is a unit vector. Again, the local x unit vector represented in a global reference frame. This is the local y unit vector in a global reference frame, and this is the local z unit vector in a global reference frame. And if we then extend our discussion a little bit and we say that the coordinates of that reference point there are, let's just call it xn, yn, and zn, measured with respect to this origin point here, well, then we can extend and we can say that that is xn, that's yn, and that's zn. Okay, let's just notionally put some brackets around that. Let's add a little filler piece at the bottom, 0, 0, 0, 1. And that is your transformation matrix. That's how we've built up our transformation matrix, right? Our 4x4 transformation matrix. And so that 4x4 matrix encodes the position through this part here, and the orientation through this part here. Okay, and that's how you build up a transformation matrix. And so when I'm in the Blender code, when I'm referencing the fact that we're building a rotation matrix, this 3x3 is what we're building. And then we're also building this matrix here for the translation. We're combining them together to get our overall transformation matrix. All right, there you have it. So hopefully that's added a little bit of color, a little bit of context to the discussion that we've either just had or we're about to have, depending on where I edit this in, around building that transformation matrix. Okay, back to the coding. Okay, so now hopefully you have a bit of an understanding of the transformation matrix. So what I want to do next is, let me see, let's come down here. Okay, so for each of our elements, what do I want to do? I want to calculate the position and orientation. All right, so we're going to assume that we're going to write a function. It's going to be called calculate rotation matrix. It's going to take in position I and position j that we've just calculated, and it's going to return two things. It's going to return the actual 3x3 rotation matrix, right, and the length of the element, right? So this function has to return, calculate these things and return it. And this is actually the biggest function we're going to write. The rest of them are all Mickey Mouse small functions. But this is where I say the meat of the work is. When we've got that, we're then going to call a different function, which is going to calculate the transformation matrix, which is really just going to calculate the transformation or the translation that has to take place to move this cylinder to the location of this element. All right, so we'll say T is going to be equal to calculate transformation matrix, and it will take the same arguments, pos I and pos j. So you can see by defining simply the position of the nodes at the end of each element, we can calculate its orientation, its translation that needs to take place, and obviously its length as well. So in R, T, and L, we have all the information we need to move this cylinder, to morph it to be essentially any one of these elements once we know the end positions of the element. So I'm going to take the rotation matrix and I'm going to take the translation matrix and I'm going to multiply those together, and that's going to give me the 4x4 transformation matrix of my element that encodes the orientation and translation of the element. Okay, so now that we have the transformation matrix for our element, we want to actually generate the element and move it. Okay, so let's go ahead and just give ourselves a note here just to say generate element and apply transformation. So we'll assume that we have another function which we have yet to write. We're going to call it generate element. It's going to take in the element scale. Remember, element scale was passed into the main function here as an input parameter, and that was at 0.03. So it's going to take element scale. It's also going to take the length of the element, which was calculated up here. It's going to take in n, which was the element number, or which was the iter that's going up by 1 here as we're processing through this for loop. And it's also going to take in, let me see, the axial force, right? So the axial force, you'll remember, was encoded or brought in as the last number within our member color CSV. So the last number of every row actually holds the magnitude of the axial force, and we're going to use that. We're going to use that when we name the element that's generated. So we'll say color, and it's going to be the color, which really is the axial force for element n, so which means basically row n, and column 4, index 4, which is column 5. All right, and let's close that out. All right, now that is going to get us an element. Let's let the output of that function equal to the element. So we're getting a handle to the element we've just generated, and now we want to move that element. So presuming that we've built this transformation matrix, in order to move our cylinder from its default position to represent the actual element, we have to just do element. So on element, we're going to call matrix world, and we're going to specify that as being equal to transformation matrix. All right, so quick recap. What have we done? We've brought the data in. We've generated a collection, okay, which is going to house all of the elements that we generate as part of this structure. We're cycling through each of our elements. For each element, we're identifying the location of the node at end I and the location of the node at end j. We're taking that information, that positional information, we're feeding it into a function that we've got to write. That function is going to calculate the length of the element and the rotation matrix. We're then going to write a new function, and we're going to calculate the translation, essentially the translate, that says transformation matrix. A better name for that would have been the translation matrix. We're going to take the rotation matrix, we're going to multiply it by the translation matrix to get the 4x4 transformation matrix that encodes the orientation and position of our current element. We're then going to take, we're then going to generate that element, right, with another function we have to write. And we're going to pass in what scale, what size those elements should be, okay, the cross-sectional size essentially, the length of the element number, and the axial force on that element. And then we're going to take that element we just generated and we're going to override its world matrix, basically, which is Blender speak for its transformation matrix, and we're going to set it equal to the transformation matrix that we defined here. So that's the first half of the story, if you like. After that, we're going to then go on and work out what build a material and set the color of the material, etc. But for now, let's just write all these functions we need to write, right? So we got to write this guy, the rotation matrix, the transformation matrix, and the generate element function. 3 meaty functions to write. So let's take a bit of a break and come back and write those in the next video.